Welcome back to another lesson in physics. This lesson is on the electric force field. Electric force is an action at a distance force that sets up an invisible force field that permeates the space around it. A charged object creates an electric field in the space around it. The field alters the space around it, and anything that enters the space will be affected by the E field. The electric force is similar to the gravitational force in that gravity is an action at a distance force that also sets up an invisible force field. The strength of the electric field is dependent upon the strength of the charge that creates it and the distance separating from another object. The electric field strength is quantifiable. We assume that a positive test charge Q is placed in the field of a charged object Q, capital Q. And we're going to place a positive test charge, lowercase q, in the field of Q. The electric field strength is then measured to be equal to the force exerted by Q divided by the test charge, lowercase q. The electric field, as you'll see in a second, is not affected by the test charge q. As you can see, when you plug in Coulomb's law for the force, the test charge cancels out, and you're left with the E field equals K times Q over the separation distance squared. The electric field strength is a vector with both magnitude and direction and units of newtons per coulomb. The direction of the electric field for a positive charge is away from the charge. So we're going to draw force lines away from positive charge, and that's what I have drawn right here. You'll see there's a positive charge, and we have these force vectors drawn away from positive charge, and that's due to the fact that we're assuming a test charge that is positive. So the convention is to use a positive test charge, and so if we had a positive test charge out here, these lines would be repelling away. For a negative charge, it's the opposite. Since we assume a positive test charge, the electric force field lines are going to end on the negative charge. The more electric field lines that are drawn around a charged particle represents the greater the charged particle. So if I added more lines to these diagrams, it would represent that the charged particle is stronger. And it does have to be uniform. So the more lines that are drawn around a charged particle, the stronger the force. So the line density reveals information about the magnitude of an electric field. Electric field lines are always drawn perpendicular to the charge, and therefore electric field lines will never cross. What does the electric field line look like for two charges? So here I have drawn two negative charges, and it sets up a repulsive electric force field in the space around it. But when you draw the lines, because we assume a positive test charge, the lines do end on the negative charge, and they never cross. And it's showing that they're being repulsed. Here I have drawn a positive charge and a negative charge, and the lines never cross, but we have the positive charge leaving. We have the force field vectors leaving the positive charge and ending on the negative charge. And the force field lines do extend out from infinity. Okay, so what I've talked about is the electric force field, and what you need to understand about electric force field lines is that they always end on negative charge. They extend out from infinity, end on negative charge, and are drawn away from positive charge out to infinity. The more dense the E field lines, the more charge the object or particle possesses. To the charge, electric field lines are always drawn perpendicular to the charge, and therefore electric field lines will never cross. Electric field lines point towards a negatively charged object and away from a positively charged object. The electric field permeates the space around the charged object, and any object placed into the electric field will experience the electric force field of that charged particle. A grand example of the electric force field would be lightning. Would be the electric force field that gets created around the clouds during a lightning storm. Scientists believe that in a lightning storm, clouds become polarized with the positive and negative charge separated out due to friction. A polarized cloud has a charge separation grand enough that it will start to attract the electrons in the ground. People have had their hair raised during a storm, an electrical lightning storm, due to the fact that the person and the objects are in the space around these clouds that have set up an electric force field. The polarized cloud sets up an E field that's strong enough to turn air, which is usually an insulator, into a conductor. And when that happens, the atoms in the air are stripped of their electrons, and we see that as lightning. Ben Franklin was very interested in static electricity, and he invented the lightning rod. And so right here I have drawn a house, and it shows his invention, the lightning rod. And what he had hoped the lightning rod would accomplish is that be the tallest place on a building, and that the lightning would strike it first, and as long as you ground the lightning rod, it would dissipate all that energy to the ground and not hurt your building or cause a fire or your appliances. And lightning rods are still used today in many buildings and houses to help prevent electrical fires and electrical surge. Thanks for tuning in.